Okay, yeah, thanks everybody for joining us here today. As Cindy said, my name is Marty Candice. I work in the HPC User Services group. So our group sort of is the first point of contact for any questions that you might have about using the high performance computing resources at SDSC. So if you are a current access user and you might be using the system like Expanse at SDSC, we're the team that you might be in touch with if you run into any issues. So happy to help with any questions you might have. Today we're presenting here the topic of high throughput computing and many task computing with the Slurm batch job scheduler, which is the scheduler we use on a system like Expanse at SDSC. And this is part of the complex series of training training series that we've started this year. And if you're new to complex, just a quick overview of the complex training program. It's a new cyber training program funded by the National Science Foundation. And the goal that we have for this project is to teach sort of non-traditional high performance computing users we sort of label as sort of non-pro with, about the sort of non-programming skills that you need to know about how to effectively use supercomputers and high performance computing resources that you'll find on sort of at the different access sites across the country. And so the topics that we cover in the series include parallel computing concepts, standard, Linux command line tools, shell scripting, security, batch computing, which is sort of a related topic we'll talk about today, data management, and a whole host of other topics as well. So if you haven't joined us for any other complex webinars, many of them for this first year have been recorded, and I'm sure Cindy has been sharing links to some of the training material, and you'll find a bunch of the topics that we've already recorded and have slide material ready to go if you want to catch up on any of these topics. And the big question is like, why is complex maybe useful for you, is sort of the question I would like to usually start out my presentations in the series with. Is the idea that we're approaching designing these training materials for each topic is, you are just getting started with moving your research workloads from, say, your laptop or desktop computer, maybe in your lab, to a high performance computing resource for whatever reason that you think that you need to move your compute workload, whether you're limited by sort of the amount of CPUs you have access to, the amount of memory, maybe you need specialized hardware like GPUs. Whatever the case is, you need to move your research from sort of your, the computer you have right in front of you to one of these more advanced resources. And the idea is, there's a lot of different components and specialized hardware that, are enable these large scale systems. And you need, if it's your first time working on them, it can be a bit intimidating to learn all the new terminology and the different components and sort of when to use what and for what reason. And that's sort of the idea for complex, of covering all these different topics about the software and the hardware that you need to understand to sort of effectively utilize these specialized resources if you haven't used them before. Okay, so today's talk on high throughput and many task computing workflows is sort of a series of batch computing talks that I've sort of started putting together for complex. And I've linked to the previous two. The first one here isn't actually labeled correctly with the right title there, but it is the same material that would be in that working title with working with the Linux scheduler. So you can click back and look at those later if you haven't seen those talks. They cover sort of how to interact with the first talk covers sort of how to interact with the Linux scheduler and sort of different things about like what policies are for scheduling and what the general concept of scheduling is and things like that. Then we talk in the second talk here about general batch job scheduling with Slurm, which is the job scheduler that we're talking about today, in terms of workflow computing. So, that's sort of the general concept of this batch computing series. If you haven't been with us along the way. But this is the goal for today's talk. So the learning goals are to define sort of what I mean by high throughput and many task computing, and try to elucidate how they're sort of different from traditional high performance computing workflows, or workloads that you'll see run on systems like Expanse we have at SDSC or some of the other Access resources. And then I want to teach you about at least two important features of the Slurm batch job scheduler that would allow you to get started with running sort of high throughput or many task computing workflows on any sort of high performance computing resources that is running the Slurm scheduler, which is the most popular, batch job scheduler. So most systems, majority of the systems today run Slurm. And so you'll run into, needing to, if you're running sort of high throughput or many task sort of computing workflows, understanding how to use job arrays and job dependency features of Slurm might be useful for your research workflows. I put also here links to the previous complex talk that I think are sort of cover sort of some of the prerequisite knowledge that I'm somewhat assuming as I work through the talk today. I will say, this is the first time I've actually put together like a formal set of slides for this topic. So it's still a bit rough around the edges, I would say. The webinars for complex are typically more of an overview or survey of the topic than say a lot of hands-on material and exercises. In the past, I've only really taught this topic as sort of a hands-on exercise in some of our in-person workshops at SDSC. And so I'm going to try to probably blend a little bit of this overview material that I have now in these new slides with some of the exercises that I still need to rework a little bit for fitting into the complex series, but that you might find useful to explore and play around with on your own if you have access to a Slurm scheduler and HPC system. Okay. So this is the overview of today's talk. We have about 45 minutes that I'll try to get through as much of the material here as I can. And depending on how far we get, I might speed up or slow down or skip over a few things here and there. But I want to start out with defining what I mean by high throughput and many task computing. And then I'll review a little bit about what we covered in the last batch computing series talk on what batch job scheduling is and what is Slurm, just in case others weren't here. And then I'll talk about these job arrays and job dependency features at the very least. I might touch on a few of these other topics at the end: job bundling, what distributed high throughput computing is, and some of the resources you might be interested in accessing, and some of these many task computing workflow manager type systems that if these Slurm job arrays and job dependencies are a little bit too simple and not sophisticated enough for your work, that you might explore using in the future. And then with every complex talk, we end at the top of the hour, and then have sort of planned ahead for 30 minutes of sort of open discussion Q&A on sort of the topic for today and anything that you want to maybe ask that's even not related if we have time. So yep, that's what we'll talk about today. Okay. So just to start with the definitions, right? This is the definition of sort of high performance computing that I gave in my original sort of batch computing talk. So high performance computing simply refers to using supercomputers or computing clusters to sort of solve advanced computational problems. And the reason that you might want to leverage these high performance computing systems, say moving from your local laptop or desktop, moving your research workloads to these systems is they're overall just much larger, more advanced systems with more computing power, more memory, more specialized equipment that can help you either speed up the time to solution for your problems. You might be able to scale up um, the, say, fidelity of your analysis of some sort of problem, or you might be able to increase the overall throughput of, if you have a type of problem where you have to solve many problems over and over again, and the solution of the problem improves with the sort of number of samples that maybe you can run, right? And so this sort of visualization here kind of represents these sort of three key advantages of HPC, where this is showing a hurricane simulation of Hurricane Katrina, which is, I guess, almost 20 years ago. Where, if you need to, this is like a time sensitive problem, obviously, where you want to solve this computation problem to try to predict where the hurricane's going to make landfall, when it comes in. And so if you need to run the simulation very quickly, you might not be able to run it with super high resolution, right? And you might need to run many different iterations of the same simulation to sort of figure out sort of the probability of the spread of where the tracks might fall as it comes in. But if you have the time or you have the computing resources, you can increase the fidelity of the simulation and improve sort of the resolution of the simulation to make even more accurate predictions, right? So it's a nice example that sort of highlights these key advantages of moving to HPC-like systems. Now, most, applications though that are written aren't designed for these large scale high performance computing systems. And that's because most applications are what we would call serial applications, where they implement sequential algorithms that run a set of instructions that operate on data in sort of a linear fashion, one after another after another. And this is sort of, if you do any programming, is where you typically start, right? And this is sort of the traditional sort of way you learn programming, if you've learned any at all. And so, but this is very limiting because some of these problems simply won't, can't be solved in this linear fashion very quickly, such as the hurricane simulation example, right? Here, I'm sort of just illustrating, it's like if you were to run your hurricane simulation in a serial fashion, you'll probably have to run it with a very low resolution and not super high fidelity. And so how good the prediction is probably going to suffer, right? And so, moving to high performance computing systems, what we really need to do to take advantage of that speed, scale, and throughput is to move to a parallel computing model, right? And so parallel computing allows you to, it takes advantage of problems that can be decomposed into different subtasks, essentially, that can be solved concurrently or, in parallel, right? Where these different tasks aren't necessarily dependent upon one another or are loosely dependent upon one another. In a certain way. Now, and when I first started in computing, there wasn't a ton of multi-core processors, say on your laptop or desktop. But today, everyone has multi-core processors. So everybody's computers and smartphones and workstations are capable of running parallel programs, right? So you can develop and run parallel applications, you don't even need a high performance computing system. You have at least a small version of one in your laptop or desktop at home, right? And but for these problems, right, there's different classes of problems of in parallelization, and that's sort of this distinction between high performance computing usually refers to these highly coupled problems that require very specialized parallel programming models, such as this hurricane prediction model or weather prediction models, versus these high throughput and many task computing models, right? And so for these traditional high performance computing problems like this hurricane or weather simulation, right? They break up the problem sort of in the physical space where you basically say, okay, run the weather simulation for a tiny region of the overall region that we actually want to model on this processor, and then take this other region on this processor. Of course, obviously those regions are coupled, and so have to not only run the set of instructions on that one region to model the weather there, but they also have to communicate sort of the pressure and wind speed that's moving across the boundaries as you break up the problem. So it gets very complicated in these traditional parallel computing models. Whereas high throughput computing is sort of the most extreme case opposite of traditional high performance computing, like problems like weather simulation. High throughput computing is really trying to tackle problems over time by completing many small, similar, independent problems that can be sort of computed across a wide variety of resources, and you don't need this sort of communication as the problem is being solved, like the weather simulation, right? In the weather simulation, you always have this exchange of data between the different processors to update sort of the pressure and wind speeds and velocities across the boundaries, where high throughput computing is essentially trying to solve what we would call embarrassingly parallel problems, which are the most natural fit for these types of high throughput computing systems. And some of the example problems that you'll see is the traditional batch processing. Say you have, I don't know, 1,000 video files that you need to run some sort of set of image processing steps on each frame, and basically each frame is independent, each video is independent, and so all you need to do is run each operation on every frame across all these 1,000 videos, and then your job is done, right? So that's like a traditional sort of batch file processing problem. Other problems like brute force search, or maybe you have a parameter sweep in some sort of model that you want to run where you're just varying one variable and keeping all the others fixed, but you have to run like a million different different values of that one parameter. Similarly, if you're familiar with Monte Carlo simulations, essentially you're sort of generating sort of random probabilistic simulation for some sort of system, and the idea is usually the accuracy of the simulations to sort of improve over time as you have more and more samples generated, or more and more simulations that you generate. And so this is sort of the traditional types of problems that high throughput computing is focused on tackling, right? And so this is one example problem here on the right that I'm showing that some of the people here at SDSC were involved with a few years ago, where there's this particle detector called IceCube down at the South Pole. And basically what they measure is these flashes of light from the interactions of fundamental particles called neutrinos that happen basically that they can see in the ice. They have these photodetectors that detect the photons as they propagate through the ice. But this particle sort of detector problems typically involved many Monte Carlo simulations to reconstruct the particle trajectories and energies and things like that they're trying to determine from what they see at the output on the detectors. And so these problems are very, each sort of simulation of a particle shower that comes through the detector is sort of an independent sort of simulation of what might have happened, right? And so one experiment they did a few years ago is they actually used up to 50,000 GPUs to sort of improve the simulation of their ice model to better understand sort of the fidelity of their detector. And so they were actually able to, use 50,000 GPUs for a couple days because this problem was so highly embarrassingly parallel. They can just, run on all types of GPUs all across the world. It doesn't matter. There's no sort of intercommunication between each individual job that would run, right? And so this is very large scale, high throughput computing problem. Now, on the other side is many task computing. And I would argue that this is sort of what we're all doing usually, is that most problems that we're trying to solve are actually a set of different, very distinct problems that are all sort of linked together in some ordered way that we have to construct to solve our research problem, right? And this is even the case with, I'm showing an example here from a group at SCSD that does sort of wildfire monitoring and modeling sort of in real time. And so they have, real world, sensors and drones and, reports from the field versus, weather sensors trying to predict the weather and how the weather will affect the fire spread across the landscape. But, the data coming from different sensors and sort of how it gets integrated into weather forecasts and sort of the geospatial data analysis, all that has to sort of get integrated at some point to run these fire simulations and predict where the fire might move next over the next day. Each step in that workflow is not as computationally expensive as the next. And so the resources deployed for each part of that workflow are variable in scale and complexity, right? And so it's I would say most people's workflows are some sense of that. There's always a lot of pre-processing and post-processing, even if you have like a massive sort of weather simulation in the middle of the workflow, right? So there's simple tasks, complicated tasks, and there's usually an ordered set of how that in order to how those tasks need to be solved in coupled together, the inputs and outputs coupled together to get to your ultimate result, right? And so this is sort of many task computing sort of sits in the middle of, I would say, high throughput computing and high performance computing, right? Okay. So that's sort of the high level overview of what we mean when we're talking about high throughput and many task computing. And so I want to do a quick visit back just to general batch job scheduling with Slurm and what that means for those who weren't here last time, and then talk about how job arrays and job dependencies sort of naturally fit into those definitions of high throughput computing and many task computing, and why that's where you would start the features of Slurm that you would start using if you have these types of problems. Okay. So, yeah, I showed this slide just to remind people that, these high performance computing systems are sort of complicated beasts with many different parts and components, and there's different scales of computing from the core level to the node to the chassis to the rack. And there's different types of storage systems and networks, and it gets very complicated. But this is what I showed last time is, there's sort of a general set of types of nodes that you need to know about. And, whenever you access an HPC system, there's login nodes. When you submit your jobs and computational workloads to the system through the batch job scheduler, right? Those jobs run on the compute nodes. There's different sets of networks. There's the different sets of file systems. And the job scheduler, which we're talking about here, runs on a different set of management nodes. So this is just the conceptual model that I presented last time that I like to try to instill as we talk about HPC systems and when we're trying to demonstrate how these workflows are executed on the system and sort of how you interact with them. So just as a reminder, this is the definition of a batch job. So it's essentially a prescripted set of commands that you execute as processes on an HPC system. They can be multi-process, multi-threaded. And basically, there's a couple different components to the job script. Essentially, you have, I think maybe it's on the next slide. Oh, no. Well, I think I'll get to that in a second here. But the key thing is every job script is essentially a simple text file that's usually specified as a shell script. So usually when you submit a job script to Slurm, it's usually a bash is sort of the most common Linux shell that you'll use. And the script is submitted to the job scheduler that will then assign the available resources that you've requested in the script to run the commands that you've specified in the script, right? And yeah, so the job scheduler just controls where that script and those commands will be executed, right? Where and when, right? Because on all these HPC systems, there's always a demand for the computational resources. So you will wait in line in the job queue once you submit a job to the scheduler, and the scheduler will sort out where and when the job runs. And as this talk sort of highlights, Slurm is sort of the most popular and scheduler used on HPC systems. And so that's usually what we have on most of our systems here at SDSC as well. And in the last talk, the essential Slurm commands that we used were the sbatch, the sq, and the scancel command. So the sbatch is the command you use to submit your job script to the scheduler. The sq is used for just viewing information about the job. So usually once you submit a job to the scheduler, usually most people run sq right after. You look to see that the job is in the queue, waiting to run on the resources that you've requested. And if you make any mistakes, especially you'll see with job arrays or job dependencies, you might want to cancel jobs and resubmit them. So those are kind of the three essential Slurm commands that we talked about last time. And yeah, this is one of the exercises we talked about running last time. And this is just the sort of your first hello world job script. Just as a reminder, essentially you have sort of three main sections of any job script that you submit to Slurm. Sort of have this first line that just tells Slurm that this is a bash script that you're submitting to be executed. The next set of lines are the Slurm directives, these sbatch directives. This is what you use to specify information about the job and the resources that you want to request, right? And so we learned last time about what a partition is, in Slurm, essentially just how most of these high performance computing systems are broken up into different partitions or queues. Essentially, they're usually used to set aside different types of resources within the same system. So here, this example job is submitting to our debug partition, which is a set of two nodes that look like every compute node that we have on Expanse, and is where you can request, a few resources to run some tests and do some debugging work. That's what it's intended for use. So that's sort of yeah, that's the debug queue there. So yeah, so you always have the interpreter line, then you have the SBatch directives that specify what you want from the scheduler. So that's what the job scheduler is going to do. And then the rest after the SBatch directives are any commands that you want to run as part of the job, right? So that's kind of the main concepts we learned about and structure of a job script that we learned last time. Okay. So job arrays. So what is a job array? So a batch job array allows you to essentially specify a single job script, but run many copies of that same job with slight modifications. Okay, so it really is a way to submit and manage a large number of similar jobs, right? And if you go back to that definition of high throughput computing, right? Many similar, small, independent jobs. So this is sort of the feature of most job schedulers that is the one that is most ideal for running high throughput computing like workloads on whatever system that they're running on, right? So and job arrays are not specific to Slurm, right? So almost all major batch job schedulers you might encounter will have a job array feature, whether it's PBS, whether it's HT Condor is another one I'll mention. What are there some, is LSS still pretty popular maybe? Anyway, but again, if you're working on a scheduler that's not Slurm, job arrays are a feature that are built into many of these job schedulers. And the main features or characteristics of an array job, so whether it's a job array or an array job, you'll hear both terminology. Again, an array job is specified as a single job script, just like we had here. It'll look very similar. It's a simple text file that's structured as a shell script. You'll have some, again, resources requests, but you'll have one extra special line that you'll see here, this SBatch array line. But we'll get there in a second. So you can submit a single job script. Each job in the array, though, once you submit the job, right, essentially that script will spawn many jobs, right? So if you ask for X number of jobs in your array, each job is assigned an indexed or an integer valued index number, right? That is in addition to the standard job ID that's also associated with a job that you submit to the scheduler, right? And that becomes important here when I show you an example of how you can sort of structure some of these workflows and say, for example, do a parameter sweep, right? Because you have this extra index that you can use as a hook to pointing to different files as your input or running different values for a certain variable in your script. Anyhow, the one major limitation usually, and why this is more ideal for sort of high throughput computing, is usually in a job array, every job has the same resource request. So every job that you run has to be similar enough to sort of fit in the same number of cores, same amount of memory, and same amount of time that you've requested from the scheduler, right? So that's sort of, you're assuming a very uniform job type while it's running. And so hopefully it needs depending on, even though each job can have, say, a different input or different set of parameters that you might be running, hopefully that doesn't affect the resources required for that individual sub job in the array, right? Otherwise, you might run into problems where some set of jobs in the array always crash because for whatever reason, the input you provided, that subset of the array needs more memory because that input is sort of out of bounds from what you can actually fit in the resources you've requested. So there's some sort of manual balancing and resource allocation that you have to do there. But if all the jobs are roughly the same, with the same amount of CPU needs, memory, and time, job arrays is the right way to go. Yeah, and so this last characteristic here is all the jobs in an array will effectively run nearly the same set of commands, and we're usually run the same set of commands and only differ sort of by the common input parameters and values that you provide, whether input variables or files that need to be analyzed or whatnot. Now, for Slurm specifically, how you create an array job is by simply adding this sbatch array directive to your job script, right? That's all you have to do. And the values that you can provide here I'm showing the value, the argument as 0 through 9. So this is showing a range of index values that I want to assign. So basically it's effectively asking if I added this to any job script and submitted it to a Slurm scheduler, it would create 10 different jobs and assign an index of 0 through 9, depending on which job in the array that index was assigned to, right? So this is one way to specify a job array. That's usually the most common that I use for is because usually on most systems, this index value is limited as well. I think that's one note that I don't quite have in my slides here yet. For example, on Expanse, job arrays are limited to sizes of 1,000, right? So essentially I could only go technically from like 0 to 999 here on Expanse, our system here at SDSC. But each system will vary depending on how the administrators of the system have configured Slurm. There's always usually a maximum, there's always, I think on Slurm, a maximum array size. And I think in most cases, there's actually a limit in the range of values you can put here. So like, for example, it doesn't really make a lot of sense to put -1, so you can't put a negative number, right? And in this case, on Expanse, I know you can't go above 1,000, right? So it really is limited to that 1,000 range. I'm not sure if that's general to Slurm, but these values always obviously have to be positive. Okay, so that's job arrays. And I kind of want to show an example, again, this sort of hybrid format of, I've done a lot of hands-on examples in demonstrations of job arrays. So I want to kind of show you what that looks like as you submit your first job array to a system like Expanse, and show you kind of how this feature is useful for creating things like parameter sweeps or running Monte Carlo simulations. Okay, so let me out of full screen mode on my end. And so yeah, this is the example that I usually use for both the job arrays and job dependencies. So I have a code that runs a simple Monte Carlo simulation that calculates the value of pi. And if you click on the Monte Carlo method link there, it kind of explains even in the Wikipedia page, like what's going on in the code. And I won't go into the details here, but essentially I'm gonna log into Expanse, download the code here, get the example job script, and modify this initial single job into an array job and show you what that looks like. Okay, just so I can show you what the mechanics of setting up that job array looks like, and how you can then increasingly add to the complexity of constructing sort of a more complex job array with this very simple example. So I'm going to, let's see. So there's a few things if you want to eventually come back and do some of the exercises yourself. I haven't quite got everything into complex yet, as I mentioned. I'm still sort of putting together this talk, but I do have the initial job script, this estimate pi in the repo that's linked at the bottom. So I'm going to copy that repository or clone that repository. No, I don't want to get clone that. Sorry, I just want the one file. Just download the raw file. Okay, so this is the same job scripts. Right? As we see here. Right, this is the estimate pi job. Now I need to go grab my copy of the code. That's what I need to clone here. And I've given, like I said, I've given this in sort of hands-on talk, more hands-on sessions. And the last update to this is from our Summer Institute here. And it has some discussion and some of the exercises that I'll try to walk through here. So I put the link in here. This is sort of where some of the complex material will come from in the future for this talk. Just haven't quite sorted it all out. What's appropriate for an hour-long session here, even though we're running really short on time. Okay. And I'm going to clone the repo. So a lot of the exercises that I usually go through in a hands-on session are in this set of links here. So please feel free to read through and try to follow along here if you want to try these here. That's sort of where these exercises for complex will come from in the future. But yeah, so I think we have everything ready. Let me try to clear up my screen a little bit. And this is the example job. So what I want to do is submit that job to the scheduler using the sbatch command. Okay. I think we're having file system problems today, so getting a few, might see some unusual behavior. Things are acting a bit strange, but that's okay. Oops. So here again, I'm using the SQ command with the -u option and feeding it my username from the user environment variable just to check on the status of the job. And just to come back from what we learned last time, I'll cancel this because I think it's going to take a bit of time. I should submit the job. One difference from, I think, the screenshot is I need to submit it to the debug queue because that'll probably run faster. Come on, live demos. Okay, so I've submitted the job to the debug queue, so it'll run for, I forget how long. I think it's less than 30 seconds with the settings I have in the job here. But the output will just be an estimate of pi from the example calculation. Oh, it's 30 minutes, so not 30 seconds. All right, I'll let that run here for a second. Now, if I want to run multiple copies of the same Monte Carlo simulation that calculates the value of pi to get like many independent estimates, right? I can go back to adding in the array directive and setting the indices just to label what my job is, right? Now, one thing I didn't mention previously as a reminder is if you look at the output files here, I'm using these special symbols to inject information into the naming scheme of the output file, right? This %x basically replicate, copies in, or what it means is like put the job name here, put a .o for output file. The %j here is the job ID, and the %N here is the node, the name of the compute node that the job landed on, right? So this is kind of just useful information to have for future debugging, or like just making sure that the output files are named differently for each different job that you run. For example, you can see here, looks like my job might be done. My estimate pi, it's the name of the job. It's an output file for job ID here. And then this is the specific debug node it ran on. Wait, the scheduler is really not behaving today. Wait, 5 minutes left. Okay, this is not running out of time. Try to speed this up here. Wait, okay. All right, so this is that output for the single job version of the estimate pi job, right? So just outputs pi and gives you sort of the runtime for each job. Now, if I go in here and submit the array job, what I actually want to do here is can actually, I think it's %. There's other symbols for other variables. One is the array job ID and one is the array task ID. So this is where you'll get I think it's the small a, if I remember correctly off the top of my head, is the index value for the array that you'll assign. So we should see one of these values, I think the small a, right, is going to be either 0 through 9 for each output file. So it's useful for using those special symbols to then label the output. Oh, let's just do 2. The debug partition only allows so many jobs to run. So you can see here with the array job, I have a job ID, but now I have that special index assigned to each individual instance of the jobs in the array, right? And if you go to the Slurm documentation, and some of the links are in the there's these special environment variables that correspond to these indices. There's the array ID. The task ID is what Slurm refers to, that special index for each job in the array. So that's this Slurm array task ID. And if you go through some of the material here, you'll see that as I work through building more and more complex job arrays, you can use these environment variables as that hook into, say, running a parameter sweep. Right? If you scroll down here, creating your first array, yeah, we create a parameter sweep over some of the different variables in this estimate pi job, right? And so take a look at that. But this is sort of how you get started with Slurm job arrays. Okay. And talk about job dependence, because those were the two big features, right? So job arrays are sort of your way into high throughput computing with Slurm on high performance computing systems. Job dependencies are your way into sort of the many task type computing workflows, where if you do have a large number of jobs that are distinct computational tasks, but they're sort of linked in the sense of like the input of one becomes the output of one becomes the input of the other. You can actually set that up using job dependencies with the job scheduler so that you can sort of set it and forget it, or at least structure this workflow to run only if the output from one job was created correctly for the next job to start, right? So these job dependencies allow you to defer the start time of any job based on what happened to another set of jobs that you've already submitted to the scheduler, right? And so that's what job dependencies are. Hopefully that's pretty straightforward. There's actually a really nice link that I put here. It's actually not directly to the Slurm documentation, but is from the NIH. They have a really good discussion of Slurm job dependencies on their website and examples and things like that. I also have some similar examples following on the estimate pi in the that high throughput computing hands-on training here, link here at the bottom, that it'll walk you through of like how do you take sort of these estimates of pi from these different jobs that you ran in an array, and then bring those estimates into some sort of simple analysis job that then runs after the array completes and allows you to sort of start using this dependency option that you use to submit jobs that need to be dependent on other jobs. And usually the most common type of dependency used is this after OK, which just means basically I submit this job and I want it to run after this other job with this job ID has finished successfully, right? And so it's all based, these job dependencies are always usually based on, at the very least, the exit code of some other job that you've submitted to the system, right? And so that's how you're able to start building these a little bit more elaborate, complex workflows for distinct computational tasks. So this is the feature in any job scheduler that's sort of ideal for this many task computing type of workload, if you might have it. Okay, so we're at the top of the hour and just over. Before I end, what I would like to just highlight is if you do have one of these high throughput computing types of workflows or workloads in your research, there are other computing resources available to you, in the US that are more appropriate than, say, a traditional HPC system and that specialize in actually high throughput computing workflows. One is the Open Science Grid. And I put the links here of how to sign up and get information about it. But essentially, it's a distributed high throughput computing system, which basically is there's this sort of distributed compute cluster based on this other type of job scheduler called HT Condor. It's not Slurm, but has all of very similar features, has job arrays and job dependencies, and you specify job scripts to submit it. But it's really designed for these high throughput computing workflows, these smaller jobs that are very similar and can scale and don't need a lot of communication between jobs, right? Or to communicate the data between jobs. And that's what it's designed to do. And so you can get a free account here. Essentially, there's a nice table here that says, hey, if your job fits in these sort of parameters, that's an ideal type of job workload that would run on the Open Science Grid. They also have a more dedicated resources. So this is from the same group, but this is sort of, you can get dedicated time effectively on OSG-like resources using HT Condor to run your high throughput computing workflows. OSG is a little bit more opportunistic, so it's more of a preemptible type of situation so that your job can actually get preempted. So you need to be prepared to restart your jobs versus this path facility. There's also other types of systems like the National Research Platform, which is, again, like OSG, it's sort of a distributed cluster, but here it's also not based on Slurm, but it's based on Kubernetes, but they specialize in providing sort of a test bed for more advanced sort of computational storage and network resources. So there's lots of GPUs, lots of different types of GPUs. There's FPGAs. They have specialized sort of input output that allows you to sort of combine FPGAs and GPUs across the country into sort of almost like a shared compute system. It's kind of interesting. So it's just another resource out there it's pretty interesting. But it runs on a different type of scheduler, right? But these features for supporting high throughput computing and many task computing is very it's much more suited for that than traditional HPC applications here. So, and before I stop on that, I did want to mention that in addition to these basic features of using job arrays and job dependencies to start structuring either your high throughput or many task computing workflows, there's actually a lot of different specialized software out there that is designed to handle even more complicated workflow problems. And so these are usually called workflow managers or workflow management systems. And there's a few out there that I just wanted to mention. They don't have a lot of information on here yet in the slides, but if you're doing any sort of Python work with a lot of the standard libraries like Pandas or NumPy and things like that, Dask is sort of the parallel version of that allows you to sort of, has its own sort of built-in custom scheduler that executes sort of these graphs of tasks. So it's very good for sort of workflows that are sort of can be high throughput, but more so these many task sort of problems that you might be able to solve with those sort of Python libraries. There's another one that I have a little bit more developed slide here is called Pegasus. Again, it's like essentially it's a framework that allows you to sort of specify and run complicated graphs of tasks and design sort of your computational workflow with the different files for input and compute that need to get put together and run in specific orders. And this actually runs on top of the HT Condor scheduler that I mentioned, but there's actually a nice hosted version of Pegasus that you can run on different access resources. So if you are interested in sort of one of these more complicated workflow management system, you have access and you have an Access account, you can try the Access Pegasus deployment that's available to you. And so I put the link here as well. And then there's other workflow managers that maybe you might be familiar with. Another one that I see a lot of is SnakeMake. Another is Nextflow if you're in sort of the bioinformatics space. But these are software that tries to go beyond the basic job arrays and job dependencies and provide sort of almost domain-specific languages to specify high throughput and many task computing workflows in a nice way. And so those are just some tools out there that I wanted to mention before we go to Q&A.